Good morning, everyone. Today we got lesson 28. So the web assignment for this is due on Friday, and the topic of this is doing double integrals over general regions, in contrast to what was done at the very beginning was just double integrals over a rectangle. So there's two kinds of main regions that we're going to consider. So you're either going to have a situation where, and this is the reason why it's going to be like this, is like the technical part is going to be setting up the limits of integration. So whereas before the limits of integrations were just numbers on both the integrals, the limits of integrations on the inner which integral is going to be in terms of functions, and then on the outer which integral is going to be numbers. So like what I'm talking about here is these two situations where you have type 1 of a region and type 2, and the variant of this is like what we're talking about is, and there's going to be a surface which is over this is what's on the ground in the XYZ plane. So you're in a situation like this, you would be entering in the region here on G of x1 and exiting here. So enter, exit. This one right here, coming in, enter the domain, and then leaving the domain. So these two, when doing these different types of integration, they correspond to these integrals here. So the first one would be like integrating over this region, and there's a surface in the air here. So you're finding volume, a surface which is above this, because the z-axis is going to be like coming out of this perpendicular. So the surface is f of x, y, so that's a function of two variables, and you're going to enter here and exit there. The other situation on this one, and so that the first in the note that like the dy, entering in a direction of y, and then finally the dx is going to be what the endpoints are. Now here on this other one, this is entering in the direction of x. So I'm moving like the pencil, and you're always going to go from left to right. So enter, exit, enter, exit, and then dx in the direction of x. And what's happening with y would have been you need to go from here all the way up to there, d. So c to d. Okay, let's look at an example here. All right, so evaluate the double integral where the region is bounded by the parabola y equals x squared and 16 minus x squared. Okay, so the first thing to do on any of these is try to draw a picture so you can get a bearing on which type of entering in the domain you would like to do. Alright, so let me draw XY plane here. Alright, so the easiest one is y equals 3x squared. Let me put that on there. So that's that function, y equals 3x squared. Alright, the other one, that's also a parabola. It's going down because of the negative right here, and then the 16 is corresponding when x is 0. On the y-axis, you would be at 16, so I put that on here. So this is run 0, rise 16, and the parabola goes down like that. Alright, so this is what's on the ground in the XYZ plane. So you want to think the z-axis is coming out of this thing perpendicular. You're about to integrate this surface is in the air up above this. Integrate this surface over this domain. Okay, now how to figure out like let me put the title on here. This is going to be y equals 16 minus x squared. So now, do you want to enter in either in this direction or this coming in like this? If you chose this way right here, you would have to have two separate integrals, one that represented enter here, exit here, and then enter here and exit there. That's going to be way more work. The easiest way to do this one is going to be coming in like this, because there's only going to be one entry point, or one entry function I should say, and one exit function. Okay, so that means I'm going to come in the direction of y first. So that means I would come in, so I'm going to have two integrals. Alright, I'm going to come in the direction of y. At first I enter in on this parabola, 3x squared. Then I exit on the parabola 16 minus x squared. The function, the surface is 2x squared y, and I've just set it up for dy. Now for dx, I need to figure out how long am I supposed to do this over the x-axis. So that would correspond to, I need to figure out what that point is and what that point is there on the ground. So for these, what you want to do is set the two functions equal to each other, and you'll find out where they intersect. So what I mean is set 3x squared equals to 16 minus x squared. From there, we end up with 4x squared equals 16. Dividing by 4, x squared is 4. So then out of here, x has to be plus and minus 2. So this point on the ground was minus 2. That one was 2. So then I need to do this integration from minus 2 to 2. So now that's our double integral at hand. Okay, so let's finish this off a little bit further. So then here, so this integral, all right, I'll leave the outer integration alone. All right, and I'm going to integrate with respect to y. With respect to y, 2x squared is a constant. All right, and then the antiderivative is y squared over 2. And you need to evaluate that from 3x squared all the way up to 16 minus x squared. And then eventually I'll have to do dx. Okay, now this is minus 2 to 2, 2x squared. Alright, so formally 16 minus x squared over 2 minus 3x squared over 2, and then I have to do dx. So on many of these problems, I would honestly suggest either using something like Wolfram Alpha, Mathematica, or something to simplify these things up, because it's going to be really at this point you can see I'm about to have to expand that thing open and clean all this up, and it's just going to be really computationally sort of annoying. So I would suggest use some kind of algebra system that will allow you to open this whole thing up, right? But I would have to sit here, foil this thing open, clean up all this stuff, and get everything going. And actually did use a computer system to clean this thing up, because just didn't want to do it. And so after you do that, you're going to end up with, so those 2's will cancel upon that, and then if you foil that thing open and clean up all this stuff, you end up with 256 x squared minus 32x to the 4th minus 8x to the 6th dx. And then even further, taking this thing for you have to find the antiderivative of this, which that's this constant times x cubed over 3, that constant times x to the 5th over 5, and then x to the 7th over 7, multiplying with the constants. And at the end of the day, the number turned out to be 69,632 by 105. So you can imagine trying to get that thing cleaned up. So I would suggest just use a computer system, an algebra system, somehow to clean these things up. Because there's the hard part is definitely, as you can see, set up the integral. The rest is and then of course remembering how we do our little integration with freezing variables and integrating with the correct, with respect to the correct ones. But just bear in mind that it's just try to use a computer algebra system to make it work smooth as you can. All right, now another one here. Okay, so let's draw some pictures. What is this? All right, so always start with this, try to figure out what is this region. So x minus 1 for the first function. So you have y-intercept of -1. It's a line with slope 1. All right, now the next one, y squared is equal to 2x plus 6. So the easiest way for me to graph that is you don't want to take a square root, because you're going to have 2 branches on that. You'll have a plus and minus thing. Solve this out for x first. So it's definitely going to be a parabola going something like this. But how to figure out exactly what you're looking at? So first you'd have y squared, subtract the 6 over, is 2x, and then divide by 2. So you'll have y squared over 2, divide the 6 by 2, you get 3, is x. Okay, so that means whenever y is equal to 0, that means you are not traveling at all. X is going to, like, not traveling at all in any height. So that means you're on the x-axis. X is going to be -3. So that tells me that there's a vertex over here. So run -3, rise 0. And now this thing has to go like this, because it's positive on the y squared. Okay, so now the region is this thing right here. Okay, so now just set this up. So what you want to think is before, like, you need to figure out, are you going to come in this way? So if you do come in that way, there's going to be two different entry functions. I would have entered here on one of them, and then on the other one I would have entered there. And you can do this, you just have to set up two separate integrals, and you'd have to figure out what that point is right there for when you change them. So you do that integral first for this thing, then plus the integral for the other one. That's going to be a lot more work. So let me label this real quick. Y squared over 2 minus 3 is x. So what I want to do though is make it as easy as possible. So I want to enter like this. Boom, entry function, exit function. Alright, so that's going to allow me just to have one single double integral. Alright, so and the surface is xy, so that's above this. Okay, now if I'm going to come in this direction, I'm going to come in the direction of x. Alright, now the entry function is going to be this one. Now you need to have this, if I'm coming in this way, what I'm entering in on is this function here first. So y squared over 2 minus 3. I'm entering in on that parabola. I exit on this line. Alright, I need that line in terms of y. Right now it says y is equal to x minus 1. If I solve this out for x, it's going to be y plus 1. Alright, so then those are my limits of integration. Now I want to figure out what my limits of integration are with respect to y. So how far do I do this on this y-axis? I need to figure out what this point is, and I need to figure out what that point right there is. Well, actually not. It shouldn't say that point, because the way that this picture is drawn, most likely this does not go like that. It kind of curves up. So it goes up like that. So it would be a point like right here. So, okay. So and then to do that, you do the same thing as before. Set the functions equal to each other. So I would set equal y. So this is like a little scratch side work here. So y plus 1 is equal to y squared over 2 minus 3, and solve this out for y. And however you get through this, the best, whatever. Like the way that I would probably do it is, I don't want to deal with the coefficient on something that I'm about to have to potentially factor. Multiply everything by 2 to clear out that 2 right there, and you'll have 2y plus 2 is equal to y squared minus 3. And then from here, take everything to one side. 0 is y squared minus 2y. I'm sorry, and when you multiplied everything by 2, that would not be 3. That will change to 6. Sorry about that. Alright, and then now when that goes over, minus 8. Now, if you can factor this, you go for it like however you can, or if not, you like run the quadratic formula on it. But this one you can see you need two numbers such that they multiply to -8 and add to -2. That's going to be 4 and 2. So we need this to be our -4 and +2. So that's our function. The roots, therefore, are y is equal to 4 and -2. So that's what this spot right here on the ground was -2. The spot up there, that must have been 4. Alright, so now our double integral is this thing right here to compute. Alright, let me just go a little further with it just to show you what has to happen next. So the outer integral, -2 to 4. Integrate this thing with respect to x. Y is a constant, so therefore it's going to be y times x squared over 2 evaluated from y squared over 2 minus 3 up to y plus 1. Then after all this is done, I'm going to have to do dy. Alright, So integral minus 2 to 4 of y times y plus 1 squared over 2. This is doing the fundamental theorem of calculus to complete this inner-which integral. And then y squared over 2 minus 3 quantity squared over 2. You're plugging that into there. And then at the end you do dy. Now, definitely, like you can see how annoying this one's going to be. You have to FOIL open both those things, sit there and clean up all this. And so at this point, just finish it off however you can. Like, so you just clean up what is inside there. And then eventually just do a calc. Like at this point, it is just a calc 1 integral. But it's just going to be a little tedious. So definitely go for some kind of computer algebra system to clean that up. All right, now something like of this sort. So if they give you this is already written as an iterated integral, so everything's put together, and if you can figure out what the antiderivative of what's inside there is with respect to y, you just go for it. But the problem is on this one, I have no idea what the antiderivative of sine of y squared is with respect to y. So this is a situation you're going to want to use Fubini's theorem, which is going to allow you, since that function's continuous, allow to switch the order of integration in hopes that you could try to figure this out. So to start something like that off, let's first try and figure out what is this region that this is over. Alright, so it's telling me that y, the function, is going to enter at the line x and exit at when y equals 1. So when y equals x and y equals 1, enter there, exit there. Alright, so let me graph these two functions. This is y equals x, and the other one is y equals 1, just a horizontal line. So if I was to enter there and exit there, what has to be is that little triangle sliver. Alright, and then x goes from 0 to 1. Alright, so the way that this is set up, it's coming in like this. Now if I switch the order of integration, I'm going to try and come in like this. So this is what I want to try to do and see if I can get to a position where I would be able to complete this integral. Okay, so now let's switch the order of integration. Function remains the same. dx coming in the direction of x. Okay, I enter at the line x equals 0. I exit at the line x is equal to y. Now when I do now how far do I have to do this over the y-axis? From 0 to 1. Okay, now we just keep going until you get to a sticking point here. This function right here is a constant with respect to x. So the inner-which integral is nothing more than just sine of y squared. That's a constant with respect to x times x. That's the antiderivative of 1. You will evaluate this from 0 to y. And then at the end I'll have to do dy. Alright. When I plug this in, evaluating this by fundamental theorem of calculus, it's just going to be y minus 0. So now the integral actually is just sine of y squared times y dy. Now that one's looking good because you could do a basic u substitution to cancel out this y right here. So I'd choose u equals y squared. Du is then 2y dy. The points at which the endpoints under this change of variables, whenever y would be plugging 0 into this y squared, u is also going to be 0. And luckily there's not any real change going on so much in this because it's 0 and 1, and squaring 1 also remains 1. So now this integral equals to, so I have 2y, so this would be, I guess I'll write every line of it. So here, so sine of u, and then you have the y, the differential is changed to du over 2y, so that cancels out those y's, so that now I'm just in a spot where I have 1/2 integral 0 to 1 sine of u du. All right. Now, antiderivative of sine is negative cosine. So 1/2 negative cosine of u from 0 to 1. Then it's 1/2 negative cosine of 1 minus a minus cosine of 0. And then cosine of 0 is 1. Those double negatives cancel out. So end answer 1/2. And so in cosine of 1, that's just some irrational number. You just leave it like that. And then plus 1. So on this one right here, this is just a practice of using the Fubini's theorem, which what you want to do is, it says dy dx. I want to make it dx dy, which you can always do if that function is continuous. But when you're doing it, you just need to change the entry of like how this integration is going on. So at the beginning, it was with y. I want to change it to x. So draw the picture and then try to figure out what the new limits of integration would be, given that you're coming in from a different direction. All right, now this wants you to find the volume of the solid under this plane and above these two regions right here. Okay, so this one has a few situations going on. First, like, what is the surface we're actually going to be integrating here? So it's written in a completely different way, but you want to think every surface that we're dealing with is always going to be f of xy equals something. And f of xy, though, that's z. So that's like the height. So if I first, let me just solve this thing out for z, so that I'm dealing with z equals 1 minus x plus 2y. So this is the surface that we're going to integrate. Now, now we need to next figure out what is the limits of integration going to be for this setting. So these also look different than before. But I want to turn them into functions in R2. So like what I want to do is solve these out for y. The first one's y equals 1 minus x. The next one is y equals 1 minus x squared. And you could have solved them out for x, but I wouldn't suggest doing that, because on that one right there, when you're going to have to take a square root. And at all costs, you want to avoid taking square roots, because that gives you two pieces you have to deal with. Okay, so now let me graph where these two functions look like. That's a line with negative slope, and it has y-intercept of 1. So, and that's a line with positive slope, so that's not correct. It is a line that looks like this. So this is 1 minus x equals y. Your other one, that's a parabola. So that is a parabola which goes down, and you're looking at something like this. And now the question is, like, would it go under that or would it go above it? And a lot of these, honestly, like, I would suggest if you're having trouble graphing them, you can use Desmos or also any of those other things like Wolfram Alpha. Put both these on there, and you'll be able to at least like get this picture drawn. Okay, so now what we're dealing with is like this little sliver right here. Okay, so now let's see. Okay, so now on this one we can choose entry from either direction, this way or that way, because there's not going to be any problems setting this thing up. There's no like anything tricky, nor is this function right here anything difficult to handle. That's just a polynomial and two variables. So it doesn't matter how we set this one up. So let's see, I guess I'll just set it up with respect, since I already have these things solved out for y, I'll set it up with respect to y. Alright, so double integral. Alright, the function is 1 minus x plus 2y in the direction of y. So enter on that line. That line was 1 minus x. Exit on that parabola, 1 minus x squared. Dx, that's going to be, I do it from here to here. I do it from 0, and if you need to figure out what the other endpoint is, like I drew it on there, but say imagine you didn't. You would set this equal to that function right there, and you're going to see that it's 1. All right, and like, so key thing is you keep seeing what I'm doing here is make sure when you have this set up with dy here, what's going on here has to be only x's. There cannot be y's here and a y there. Okay, now you just complete this as we did before. So outer integrations from 0 to 1. Antiderivative of all this thing with respect to y. Antiderivative of 1 is just y. The next one is x times y, because x is a constant. The next is 2 times y squared over 2. And then you need to evaluate it 1 minus x and 1 minus x squared. And then at the end, I'd have to do this thing dx. All right, just write one more line before before you would go to like some kind of algebra system to clean this thing up. So 0 to 1. So 1 minus x squared, and plugging those into here where the y is, minus x times 1 minus x squared, plus, cancel out those 2's, plus 1 minus x squared, quantity squared. So 1 minus x squared, quantity squared for going in there. Now, minus, so this is now fundamental theorem of calculus. You're going to plug in 1 minus x into that. 1 minus x, 1 minus x for that y. And then plus 1 minus x quantity squared. And then all this would be, all this would be dx. And then from there, just finish it off Calc 1 style after cleaning it all up. All right. So now, just overview of all the properties of what we have here. So you can always split things with addition. If you have the sums of two different functions, you can never split things with respect, like if this is multiplication. Only in very, very certain circumstances. So what I'm saying is never does this go down, just like in Calc 1. Say whatever, dA. So never is that kind of situation going to happen unless you're dealing with some kind of exponential function, and that's playing off of properties of the exponential. Never can you can never do this unless only in very certain circumstances. But addition always behaves well. That's coming from that this is some kind of just adding up areas is all that's going on here. Constants, we've been doing that over and over. Those always come out. Situations where one function is bigger than another one, just like in Calc 1, the integrals would be bigger. This one right here is talking about something like if you had a domain which was two separate domains, like imagine like one looked like this and another one was over here. So here's D1 and here's D2. Provided these things do not overlap, so if D was the union of this one and that one, you could do the integral over this and then add to it the integral over that one right there. This one, this is telling you, this is just a formula for area. So if you integrate the number 1, the constant 1 over a surface, you're just going to pick up the area. Now this other one is talking about something, if you have a function that's bounded, and so if you need to bound an integral, so, and where that's coming from is this, what's going on here down here with this average. So you can imagine this average has to be like you would bound this function a of d multiplied by that constant over this integral. So yeah, let's not get in. I want to make this thing as simple. No more proofs in this course or anything. But where this is coming from is this formula right here. So this is an average of an integral, and you did something like this in Calc 1. And what does this average actually mean geometrically? So this is, when you take physics, this is your center of mass. So this is the center of mass of a function. Yes. So and then this problem down here just wants you to compute the average over this triangle. But where you're going to see this though is in physics, where they're dealing with center of mass. Okay, so let me draw this triangle here first so we can see what's the domain. All right, so 0, 0, run out 0, 2, rise up 2, 4. All right, and I want to find the average value of this function over this triangle, which that's going to be what is the center of mass. Okay, so, and that form an A of D, that's the area. So for us, we need the area of that triangle. So area is 1/2 base times height. 1/2 the base is 2. The height is also 2, so I get 2. Okay, so that's what's going to be, so there'll be a factor of 1/2 sitting out in front of this thing. So 1/2, some double integral. All right, the function is x times y. Now, it doesn't matter which way I enter or exit on this. I'd probably just enter, like, just because to make it as simple in our heads as possible, because we like to think of functions as y equals. I would probably come in on this one on dy. If I'm coming in on dy, I'm going to enter at the line y equals 0, exit at this line right here. All right, that line, using college algebra type techniques, that's a line with slope 2, y-intercept of 0, so that line actually is represented by y equals 2x. So therefore I enter at y equals 0, I exit at 2x. Now x is going to run from here all the way over to there, so x goes from 0 to 2. So then that's the double integral that we're about to be messing with here. Let me work this one out a little bit. So 1/2, 0 to 2. Integral of that with respect to y. X is a constant. So then times y, antiderivative of y, which is y squared over 2. Evaluate from 0 to 2x. And then do dx. Alright, since this one's so simple, let's finish it off real quick. Okay, so let me cancel off those two. Let me leave those two twos. Those two twos come together and produce a 1/4 in the front. 0 to 2, and then I have x multiplied by. You need to put that inside this function using fundamental theorem of calculus. You would achieve 4x squared, and then minus 0, because when 0 goes in, y squared is 0. All right, now when I'm canceling 4's, all coefficients are out, and now my integral is 0 to 2 x cubed dx. Antiderivatives x to the 4th over 4 from 0 to 2, and then 2 to the 4th over 4 minus 0 over 4. 2 to the 4th is 16, and then 16 by 4, and answer is 4. Alright, so that's all the problems for today. I hope you have a great day. Thank you very much.